Hello everybody and welcome to part 7 of this tutorial series where we'll be getting into the architecture of Cartesi and talking about this more in depth compared to what we've gone over in previous videos. Now I'm going to start by giving you a general overview and summary of the main components that we're already familiar with, just to make sure everyone is up to speed and remembers it. Then we're going to dive into some of the more complex components. For example, we're going to talk about consensus, and we're going to talk about how Cartesi rollups are different than other types of rollups and why that's important for you to understand. So let's begin by going through a high-level overview of the main components of a Cartesi application. So we have Cartesi rollups, Cartesi Machine, the dApp backend, and the dApp frontend. Now, as we've seen here, and we've looked at this diagram before, what we're responsible for building is the front end and the back end. The rest of the components are already built for us, and they make up kind of the Cartesi rollups framework. Now, as we saw in the previous video, Cartesi rollups itself is a set of on-chain and off-chain components that implement the optimistic rollup solution. Now, the on-chain components include smart contracts, right? So for example, input box, part of Cartesi rollups. Our dApp factory, again, we need to deploy that onto the target network. Then we have the Cartesi machine. Now this, as we know, is a virtual machine running an entire Linux operating system in which the dApp's backend is executed. Now there's some more details related to this. For example, it runs a RISC-V architecture, which is actually able to be hashed, allows us full transparency, and gives us some features of the Cartesi machine which are important and actually kind of go into the security and details, implementation, etc., which we can talk about later. Regardless, the Cartesi machine is where we run the dApp's backend. Now this is where we have the state and verifiable logic, which corresponds to the smart contract. This is what we wrote in Python and what we can write in pretty much any programming language that runs as a Linux application. Then we have the front end, works the same as any other front end for a decentralized application. We built this in React and JavaScript. So here is the general architecture that we're already familiar with. All right, so now let's dive a little bit deeper into Cartesi nodes. Now the Cartesi node itself is the L2 component that consists of the combination of the Cartesi machine, that's what runs our backend, and some specific middleware. Now what this middleware does is actually manage and controls the communication between the on-chain components and the off-chain components. So this middleware, what it does is read data from the L1 smart contract. This is what's running on-chain, and this would be the inputs, for example, that are sent to the Cartesi machine, and it's then sending them to the machine to be processed. Then whatever the Cartesi machine spits out, so a voucher, a notice, a report, etc., it can then publish that result back to the blockchain. So that's kind of the basic idea on how the Cartesi node works. You have the middleware, which is actually communicating with the layer 1 smart contracts, and then you have the Cartesi machine itself, which is running the backend in an isolated environment. Now, as we see here in practice, there are two different types of our Cartesi nodes: user and validator nodes. Now, each of these interact with the on-chain rollups in a different way and thus run different types of Cartesi nodes. So the user or reader nodes. Now, these are the most basic, and what these are doing is just advancing the state of the off-chain machine and making that state publicly available. Now, anyone can run a user or reader node. Whoever is interested in the state of the decentralized application is able to run one. And that way, they can always have up-to-date information about the Cartesi dApp. They also could use one that was made publicly available. Then we have a validator node. Now, the validator node is doing something a little bit differently. What this is doing is not only keeping track of and advancing the state of the off-chain machine, its instance of the off-chain machine, it's also trying to fight dishonest validators. So pretty much what it will be doing is checking at every single epoch if the state that was submitted to the blockchain matches the state that it has. So a bunch of these different validator nodes will run. They'll all come up with what they think the state of the Cartesi machine currently is, or what it should be next. And then if there's some kind of dispute, they will resolve that dispute by taking part in some kind of verification game. We'll talk about that later on, but the idea is just like we have nodes or we have miners that are running on Ethereum, we can have the same thing, but specifically for our Cartesi dApp. So we can run as many validator nodes as we want. Anyone else can run a validator node, and that means we have our own kind of set of infrastructure for our specific decentralized application that still is decentralized, right? Anyone can run a user node, anyone can run a validator node, and these validator nodes are going to be checkpointing state updates on the blockchain and ensuring that all of the states that are being received from the other validator nodes are indeed correct. So very similar to how a normal blockchain network works. In this case, it's just for our specific decentralized app, which we'll talk about a bit later. Now this leads us a little bit into epochs. So pretty much what we want to avoid doing here is constantly interacting with the blockchain if we don't have to. So what we do is we have these validator nodes that do not checkpoint every new state update. What they do is they're updating or checkpointing batches of state updates at the end of a specific epoch. So as you can see here, it says in order to end an epoch, all validators need to reach a consensus about the state of the machine after processing all of the batched inputs. So validator 1 takes all of the batched inputs in this epoch and determines that at the end of all of these inputs, the state of the machine is X. Then you have validator 2. If they come to the same agreement, okay, we're good to go ahead and checkpoint what the state was at this point in time. However, if they were to disagree, then they have to take part in some kind of verification game, and they have to dispute this by actually running some computations on the blockchain, which we're going to get into in a new section. So that's kind of an overview of the main things we already know. Now let's also just talk a little bit about sending requests, so the advance and the inspect. Now, we already know how these work because we've used these quite a bit, but there's two ways we interact with the Cartesi machine. We have advance and we have inspect. Now, when we advance, what we're doing is we are sending an input using the blockchain network to our decentralized application. The important thing here is that all of our inputs are logged on the blockchain, so they are managed securely by layer 1. Now, these will be batched and they'll be processed by our validators and by the Cartesi nodes, but the idea is anytime we want to advance or modify the state, we do need to send a transaction, and we do that by sending an input. Now, if you're interested in exactly how this works, we're using a JSON RPC call to the input box contract. We don't need to get into that too much, but again, the advantage here is that we don't need to actually execute all of the logic on the blockchain in a smart contract like we normally would. We can send whatever data or whatever advance request we want through this input box contract, and then all of the processing, which can be quite large as we have seen, can be handled off chain and then logged on chain. Then we have the inspect request. Now this is an external HTTP API, very simple. It's a call to the Cartesi node to simply read what the state of that machine is. Now we can see that there is a video here. It kind of goes through how this works, so feel free to watch that. And it kind of talks you through how you actually add an input, how you do an inspect, etc. So if we want to advance the state, what we need to do is actually send a request using our blockchain network. So in this case, the Ethereum node, we trigger the advanced state request, and then that hits the Cartesi node. So we have this in-between step where we need to actually go to layer 1. However, if we want to send an inspect, we can go directly to the Cartesi node because no state update can be invoked with an inspect request, only with an advance request. So inspect, very fast, you go directly to the node. Advancing, you still need to go through layer 1, and you need to have that input stored on layer 1. It will then get batched into an epoch, and it will be validated by the validator nodes that are running on the Cartesi network, or for your Cartesi dApp, sorry. All right, so now let's dive into the Cartesi machine itself and talk about this a little bit in more detail. So if we were running a normal decentralized application that wasn't using Cartesi and wasn't running on layer 2, then what we would be doing is relying exclusively on smart contracts that are on layer 1. Now, these face severe constraints on the amount of data they can manipulate and on the complexity of the computations they can perform. Now, these limitations manifest themselves as exuberant transaction costs, and even if such costs could somehow be overcome, it's extremely long to run different computations. If you don't believe me, go and try to write a simple smart contract that does something like 100,000 loops, okay? Pretty trivial to do that on a standard computer. Try to do that on the blockchain and see what happens. Anyways, the idea here is that in comparison, our decentralized apps running inside the Cartesi machine can process relatively unlimited amounts of data at a pace of over 4 orders of magnitude faster. Now, this is possible because they're running off-chain, so they are free of the overhead imposed by the consensus mechanisms used by blockchains, which is really what slows them down. Now, the double-edged sword here is that the consensus mechanism is also what keeps them secure, but when it comes to doing computations and running applications, not just logging transaction data, it causes things to be very slow and very expensive. Now, in a typical scenario, what's going to happen is our decentralized application will execute the Cartesi machine off-chain and report its results to the blockchain. Different parties do not need to trust each other because the Cartesi platform includes an automatic dispute mechanism for the Cartesi machines. Any interested party can read the computations that are happening off-chain, and if they don't agree on the result of those computations, so essentially the state update of the machine, they can enter into a dispute, and this mechanism guarantees that it will always be won by an honest party. Obviously, there's a lot of math that goes into this, but the reason why this is able to work is because of the three main properties of Cartesi machines. First of all, they are self-contained. Second of all, they are reproducible, and they are transparent. So that means given the same set of inputs, the Cartesi machine will always reach the same state or the same output. So that's important because that means it doesn't matter when you run your Cartesi machine, who's running it, in what environment, etc. It's always going to reach the exact same output, and it's verifiable that given a certain set of inputs, this output was reached. And we're going to talk about that by going into something known as the state hash, which is kind of the main idea here behind the Cartesi machine. Now, obviously, there's a lot more information that we could dive into here, and you can see that there's some pretty in-depth documentation about the Cartesi machine, but I think the thing that will kind of bring this full circle for you is looking at something known as the hash view, or the state hash, okay? So hash view of state. So one of the goals of moving computations off-chain is to allow them to manipulate vast amounts of data, so much data that it becomes economically prohibitive to explicitly store them in the blockchain. Nevertheless, for smart contracts to delegate computations off-chain, they must be able to specify the computations, their inputs, and then reason over their outputs. So this is key to solving the contradictory goals in the clever use of cryptographic hashes. Now, the basic idea here is that the Cartesi machine itself is transparent. So that means everything from the ROM, the RAM, the flash drivers, general purpose registers, all of this complex computer architecture stuff that I don't know that much about is available for anyone to see. Now, what that also means is that at any point in time, we can take all of this information, we can run it through a hash function, and we can generate a unique cryptographic value that essentially encrypts or encodes the entire state of the machine. Now, obviously, I am oversimplifying this, and I highly recommend you read this for more information on how it works, but the idea is at any point in time, I can go to my Cartesi machine, and I can ask it to give me a hash of the state. Now, only this specific state will generate the hash that it gives me. And this hash is the main security feature that we use. So for example, if we have a certain set of inputs, those inputs will lead us to a specific state. We can then hash that state, and we have essentially an encoding or a representation of what it is with very little amount of information that we need to store or be transmitting. We don't need to actually tell someone what all the ROM is, the RAM is, the flash drives, what could be multiple gigabytes of data. We just take a hash of all of this information, and that encodes this state. So now another Cartesi machine or another Cartesi node can actually check the state of its machine, and it can see if it matches the state that we have. It can do that without having to have all of this information. It simply needs the hash of the state. So let me hop over to the whiteboard here and I'll explain more about what I'm talking about. All right, so I'm on the drawing tablet here and I'm going to go through a bit more of how this hash view of the state works and then talk to you very briefly about the verification game. Now keep in mind, this is very, very high level, grossly oversimplified, so I just want to make sure that's clear. If you are really interested in this, please read through the white paper and some more of the documentation that I will link in the description. So first of all, let's say that we have a blockchain, okay? So this will be B, this is our blockchain network. Then we may have, say, two Cartesi nodes, which are running on layer 2 and are keeping track of the state of our decentralized application. Now this blockchain itself is tracking all of the inputs that are sent to our decentralized app. So it might have input 1, input 2, input 3. These are all actually logged on the blockchain. Now what will happen is these inputs will get sent over to our Cartesi nodes and they'll be executed by the Cartesi machine. So these machines here will be keeping track of the current state of the machine and they'll be updating the state after each input comes in. So input 1 gets sent over to machine 1, it then updates its state to represent the change after input 1. Same thing happens here, input 1 gets sent to machine number 2, and machine number 2 updates its state. Now after an epoch, so a certain batch of these inputs has been sent, what's going to happen is both of these nodes, assuming they're validator nodes, are going to report what their current state is back to the blockchain. Now they can do this efficiently because they can take whatever the state is, so let's imagine all these lines here are the state, they can effectively bundle it up and they can take a hash of this state. So they can hash the entire state and then they can actually submit the hash of that state to the blockchain. Now this is valid because only one given state will generate one given hash and it's infeasible to find what the hash of the correct state would be. I'm not going to dive into this too much. This has to do with hash functions and cryptography, but the basic idea is they're going to log after an epoch what they believe the current state of the Cartesi machine is, and they can do that using the hash view of the state. Now what will happen, let's say that this guy logs, the hash 123 and this guy logs the hash 456. In practice it'd be much larger than this. I'm just using simple numbers. Is at this point they've disagreed on what the state of the Cartesi machine should be after this batch of inputs. So what needs to happen is we need to have a dispute resolution where we figure out what the real state should actually be. Now, what would have been happening is the application beforehand, so the smart contracts running our Cartesi dApp, would be logging what the state is after every single epoch. So it would say something like epoch 1, and the state is equal to, X, Y, Z, right? Epoch 2, same thing, you get the idea. And it's keeping track of all of these states that have been agreed upon, that had a consensus from these Cartesi nodes. So what we do is we don't need to process every single transaction that's ever been involved in our Cartesi dApp. We simply go to where we know we had finality, so where we know the state was agreed upon and there was consensus, and then we start processing the inputs that are not agreed upon, so the state update that was not agreed upon, on the blockchain. So let me just really clarify this again because I know it's a little bit confusing. Pretty much, these Cartesi nodes here are constantly keeping track of the state of our decentralized application. They're logging that back to the blockchain, and when they both agree, they say, okay, well, that's good, the state is final, now we can move on and we can process the next set of inputs. Now, the blockchain itself will just assume that everything that's sent from these nodes is correct so long as they reach consensus on that. It doesn't need to actually process any of the computations unless there is a dispute. So at this point, where there is a dispute, where these two hashes or these two state updates don't match, what we do is rather than processing the computation off-chain, we actually process part of the computation on-chain. Now this is more expensive and it takes longer, but we utilize the security components of layer 1 to ensure that the state update that we're about to log onto the blockchain is indeed correct. So again, basic idea is when these two things do not agree, so when our nodes do not have a consensus on what the state update should be, we actually push the computation onto the blockchain and we compute the new state update directly on the blockchain. So we ensure that since it's computed there on the blockchain, that it's going to be correct and valid, and that we log what the next state update actually should be. So that is the very, very, very high level overview of how the kind of verification or dispute process is done. Whenever we disagree on what the state of the Cartesi machine should be, these two parties will play something known as a verification game. They're going to interact with the blockchain. The blockchain is going to determine where the last known state that valid was. It's going to start from there pretty much, and it's going to take whatever the new inputs were that have not been agreed upon, so the state after those inputs, and it's going to process a partial computation on the blockchain to ensure it gets the correct state. It's then going to log that on the blockchain, and then we're going to continue moving on to the next epoch. So one of the main advantages of this system that you're seeing here is that we're only performing computations on the blockchain when they need to be performed to essentially resolve a dispute. And we're only doing a partial computation, which is much quicker and faster to execute, rather than rerunning the entire Cartesi machine, for example, directly on the blockchain. Again, this is a bit more complicated to really understand how this works at a deeper level, but the idea is we already know what a final state was at a certain point in time. We can essentially start from there, just compute the part of the computation that was disputed, and then we can log that result directly on the blockchain, and we can have that immutability component where the blockchain says, hey, at this point, after these inputs, this is the state. And then we keep going and we move to the next epoch. Now, another advantage here is that we only need to have consensus among the involved parties. So rather than the entire network verifying every computation, the consensus is just reached among the parties that are directly involved in the transaction. For example, if two users are interacting in a Cartesi-based application, only those two need to reach an agreement on the outcome of their interaction. It doesn't concern the entire Ethereum network, for example. So that's a little bit about how the verification actually works here on Cartesi and the dispute mechanism. Again, this all has to do with those main properties of the Cartesi machine and the fact that we can actually hash the entire state, We then can use the blockchain when we need to actually resolve a dispute, and we can have the finality there of a batch of transactions, which is our epoch. Okay, now let's head back over to the computer and talk about the last few components. So the last thing I want to go over here is something known as application-specific rollups, which is what Cartesi implements, but in order to understand that, we'll quickly just recap a blockchain rollup. Now, this is a scalability solution that pushes complex computations off-chain. This means they run in a separate computing environment outside of the main or base layer, such as Ethereum. Now, when we use rollups, the blockchain's role is simply to receive transactions, and to log them. And as we saw, on occasions where there is a dispute or a disagreement, then we can actually execute the computation on-chain, but we don't need to do the entire thing. It can be a partial computation where we can verify on the blockchain network what the correct state should be. Now, doing this really drastically improves the scalability of our applications because we're able to compress data and we can increase the number of transactions that the blockchain can process because we're taking those heavy computations and moving those off chain. When we're just using the blockchain for the sole purpose of logging transactions, it can handle much more data much faster than if we were executing all of the computations directly on chain. Okay, so how does a rollup work? Users interact with the rollup through transactions on the base layer. They send messages, in this case they're called inputs, to the rollup on-chain smart contract to define a computation that they want to be processed. In this case, it could be an advanced request of the computing environment. Then interested parties run an off-chain component, in our case a node, that watches the blockchain for inputs, understanding and executing their state updates. Once in a while, the state of the machine is checkpointed on the blockchain, at which point the state is considered to be finalized. So once the state is finalized, that's when we can actually say that a notice is correct and we can execute something like a voucher from Cartesi. Now, there's two main types of rollups that we use: zero-knowledge rollups, ZK rollups, or optimistic rollups. Now, a zero-knowledge rollup uses something known as a validity proof. What this pretty much means is that with every single transaction it submits to the blockchain, so every rollup, it's going to actually produce a validity proof that can be used to verify that what information it is submitting is correct. This takes a little bit more time. It's a bit more complex, but the benefit here is that we have instant finality. So as soon as something is submitted to the blockchain, we can immediately say that it is indeed correct. However, it can be a bit expensive to actually verify these rollups because you have to do those on-chain, and it can be difficult to produce validity proofs. Then we have optimistic rollups. Now, optimistic rollups use something known as a fraud proof. And really the general idea behind an optimistic rollup is that we're going to assume that every single state update that is sent to the blockchain, so those kind of batch checkpoints, are valid unless they are challenged. So rather than requiring people to always kind of submit a proof and verify that what they're submitting is correct, we just optimistically assume that whatever is submitted to us is indeed correct, and then we only challenge that, or we only verify that, if it is challenged. So this actually removes a lot of the load from the blockchain because we're only utilizing the chain for computations when we have some kind of challenge or when parties disagree, which ideally will not be too often. Now, the way that this actually reinforces by using financial incentives that reward honest behavior. We don't need to get into that in this video, but that's the basic idea. So moving into Cartesi's version of optimistic rollups, this uses something known as an interactive fraud proof. Now, the idea here is that we are hardly ever actually having to do computations on the blockchain because either there are no disputes and no computation takes place, or if a dispute occurs, it only needs to compute a single instruction to distinguish between misbehavior and honesty. In either case, the results themselves are always computed off-chain, and as a consequence, the computation involved can be massive. So that's kind of what I was talking about. We only need to do a partial computation. I don't want to get into that too much because it's a little bit complicated on how that works, but the idea is what we're doing on-chain is very limited, and if a dispute does occur, it's not that expensive to resolve. So now we can touch on something known as application-specific rollups, which is exactly what Cartesi implements. So normal rollups, say like Optimism, Arbitrum, etc., at least the ones you might be familiar with, are kind of a one-size-fits-all solution, and they still actually suffer from a lot of the traditional computation issues with a normal blockchain network. Now, they actually are really limiting in terms of how you can build your applications, and they're good, generally speaking, for a lot of different types of applications, but they're not great for a specific type. Now, Cartesi itself has application-specific rollups, which means that you can create your rollup however you want for the specific type of application that you are building. So this allows you to optimize performance, functionality, etc., and just gives you more efficiency and flexibility than a standard rollups framework. Now, a lot of the reason why this works is because of the Cartesi machine, the consensus mechanism, etc. But Cartesi has this integration with Linux, right? As we know, that's why we were able to write our smart contract in Python or really any language that we want. And it gives us the ability to be very dynamic and flexible with how we design our application. As you saw, we can design our own protocol. We can specify what we want to do with inputs, how we're going to handle inspect requests, and we can do this in a very familiar development environment. Now, part of the reason why this works is because we have off-chain computations with on-chain security. So as you saw, Cartesi enables the complex computations to be performed off-chain while still maintaining the security guarantee of the blockchain. Now, this balance is achieved through the dispute resolution mechanism, which we've talked about, which differs from the general approach of other rollups where computations are simplified to fit the blockchain constraints. So in other types of rollups, you have to write your computations in a way where they could be executed on the blockchain. With Cartesi, you don't need to do that because of the way that the computations are verified. We can write them however we want, as you've seen, using our traditional program languages, and then they can still be verified on the blockchain using a partial computation that is executed on there. So with all that said, it just makes Web3 development a lot more accessible because again, you're designing something for your specific application needs. You're not trying to fit into the constraints of a blockchain network or of a pre-built solution. You can do really whatever you want. So with that said, that's kind of going to wrap up this video. I know there's a lot of stuff here. I went through a lot of complex topics and I didn't make it 100% clear, but I wanted to give you something to chew on, something to think about, and kind of encourage you to go to the Cartesi documentation if you're interested, read more, go through the white paper and really understand how all of this stuff works. I think it's really interesting. I'm still really just getting familiar with some of the more complex mathematical concepts, but I think it's really interesting how Cartesi differs from some of the other rollups frameworks and the type of applications you can build with it. As you've seen in this series, and as we've kind of gone through this documentation, it's really unlimited the type of apps you can build because of this Linux environment and the unique way that Cartesi handles rollups in the interaction with the blockchain. So with that said, I'm going to wrap it up here. I hope you found this helpful, and I look forward to seeing you in the next video.